Okay, so we just talked about sigma bonds being one type of molecular orbital. Pi bonds and pi molecular orbitals are the other type that you'll see. These happen when you have two p orbitals overlapping above and below the bonding axis. So what this would look like is, let's say we have two oxygen atoms this time. Okay, so these are p orbitals of an oxygen atom. Each one has one electron in it. Okay, the nuclei are right here on the bonding axis. When these bonding orbitals are formed, instead of being symmetrical over the bond axis like we saw before, they make these blobs above and below the bonding axis. Okay, so here's the nuclei of one oxygen and of the other. And then the electrons can inhabit either one of these two blobs. Okay. One of the wacky quantum mechanical things, though, is that, I can have one electron in one blob and one electron in the other. The next moment, both electrons can be in one blob, and then the next moment, both electrons can be in the other, right? So the way that electrons move around and about, we don't really fully understand. So here's the challenge that I want you all to try right now. A double bond is formed when a sigma and a pi bond together make a covalent bond. Okay, so I want you to try to draw a sigma bond between two overlapping p orbitals and then the pi bond between two overlapping p orbitals, and show what that would look like to represent a double bond. Okay. After you do that, think about this question. How does a molecular orbital differ from an atomic orbital, what we talked about at the beginning of the first video, and why is this distinction important? Okay, after you've drawn that picture and answer those questions, wave me over and explain to me what you came up with, and we'll see how that goes. So go ahead and pause the video, and then when you come back, we're going to talk about hybrid orbital theory. Okay, so hybrid orbital theory is a little bit complicated, but my warning is that don't worry too much about it. I'll tell you exactly what you need for the test, but I am going to walk you through the whole concept right now. So one of the problems with molecular orbital theory is that it says that s and p orbitals can't mix and match to make a bonding orbital. So that's problematic because most of your molecules that are made by bonds between anything and hydrogen mean that you're going to need to overlap a p orbital, like here on carbon, with an s orbital. Okay, so that we know that happens. So molecular orbital theory didn't account for that. Hybrid orbital theory will try to account for that. So let's look at our first example of a hybridized orbital. We're going to use methane as the example molecule. Okay, so CH4. Okay, we know that carbon has 4 valence electrons. If we were to draw out the Aufbau diagram for carbon and write out its electron configuration, we would end up with 2s2, 2p2 being the last little bit of its electron configuration. Okay, it turns out that this is not really how the electrons exist in carbon. It is more stable for the atom to take one of these electrons that's in the 2s orbital and promote it up to one of the 2p orbitals. Okay, so if you were going to draw out the Aufbau diagram, you'd have your 2s here and your 2p here, 1 box here, 3 boxes here, right, and an electron in each box. Okay. Now, it gets a little weirder than that, though. Not only does it promote an electron, it needs to make sure to really be balanced that all of these orbitals are the same. So instead of distinguishing between 2s's and 2p orbitals, it blends them all together into one type of orbital that's called sp3. Okay, sp3 is made from 1 s orbital and 3 p orbitals. Okay, all together, you're going to have 4 sp3 orbitals. All right, and so that's what these little green blobs are. They're an sp3 orbital. Okay, so carbon has 4 sp3 orbitals. Each of those can make a bond with the s orbital on a hydrogen. Okay, and you end up with 4 sigma bonds or 4 single bonds here between carbons and hydrogens. So that's the basic introduction to hybrid orbital theory.